perspective. What means this result? The result means that we have an effect, we suppose that we have an effect of clustering of nanotube in the semi-dilute regime. And now we are going to try to understand this phenomenon of clustering of nanotube. To do that, we have developed a specific technique in our lab, and we have combined two experiments, rheology with electrical conductivity. We have designed a specific cell, and this is not a conventional cell in rheology. This is a ring cell. So why a ring geometry? First of all, we have to, for the electrical conductivity, we have to isolate the cell of the rest of the machine. So here you have the Teflon back rings. And on the other hand, if you, for example, if you want to study the influence of the pressure on the clustering of nanotube, we have to define a constant shear rate. And in order to have a constant shear rate, we are obliged to do a ring geometry. We could have used a cone plane geometry to have a constant shear rate, but it's difficult to develop a cone plane geometry due to the isolation of the cell for the electrical property. So, and here you have the connection to the electric analyzer. So, if you have some interest in this domain, when you look at the literature, some experiments are performed by applying a pressure experiment. But when you try to do a pressure experiment, first you have to put in place the sample in the So what is the influence to put in place the sample on the rheology? So, and here, rather to study the influence of pressure, we have used an elongation deformation in the first part of the experiment. So actually, we put the film, the sample of about 1 millimeter, and we applied, by the displacement of the upper cell here, we applied an elongation deformation of about 5 reciprocal seconds. So the total deformation summed by the sample is 0.3, so we can calculate the different Becquerel number, for example. So the principle of this experiment, first, when we put in place the sample, we apply an elongation deformation, and after that, I'm going to study the restructuration of the network by follow the variation of the complex shear modulus. The first experiment was following. The frequency used was 1 radian per second at the concentration of 0.2%. I remind you that at this concentration, we have a deviation of the Dirichlet theory. And what we observe a small variation of the complex shear modulus, but we have a variation. And we have a strong variation of the conductivity. Here we have the conductivity of the PDMS matrix. So we can admit that when I put in place my sample, I have totally destroyed the network. And we observe a structuration of the network and a variation of the conductivity from this value to this one. We have 3 or 4 decades of variation of the conductivity. And you can see the time scale. Here the time scale is about 100 hours. This deformation, this is important, the deformation is 5%. And I can admit that at this deformation, I am in the linear regime. Now at higher deformation, about 60%, first question, I'm still in the linear regime, I don't know. we will check later. And you can see here the strong variation of the complex shear modulus and the conductivity. And you can see that the time scale is quite different. It's shorter than the time we observed in the previous slide. And the typical time is about 10 hours. And you can see also the variation of the G prime. Here you have a liquid viscoelastic behavior. G prime is lower than G double prime. And here you have elastic behavior because G prime is higher than G double. So, what if we admit that this variation is due to the network formation due to the nanotube, but the aggregation kinetics depends on the deformation. At higher deformation, here 200%, at this deformation I'm sure that I am in a non-linear regime. The kinetic of aggregation is accelerated. The characteristic time is a few minutes, but we have a small variation of the conductivity and the complex shear modulus. And G prime is lower than G prime. At this deformation, I am still in the liquid viscoelastic regime. So at this deformation, actually I have a competition between clustering and between breakup of this cluster. And because I am in the non-linear regime, and this non-linear regime leads to this particular period. In this slide, I have summed up the different results. So here you have the variation of the storage modulus versus time. So you can see that the aggregation of nanotube strongly depends on the deformations that you apply. And you can see that the transition between the linear regime and the non-linear regime is about 600–100% deformation. And the time scale of aggregation depends on the deformation that you apply when you are doing your experiment. This result, and you have the same result observation for the conductivity. But for the conductivity, we have some experimental limit for deformation higher than 200%. So these results are qualitatively in agreement with the recent work published in Journal of Urology. And this guy developed a model, and the model shows that the carbon nanotube aggregate at low shear, and the level of entanglement decrease as the shear rate increases. So we observe in dynamic conditions the same behavior that I have observed in steady shear flow. About the transition between linear and non-linear regime, this is a variation of the complex shear modulus and the conductivity divided by the value of the equilibrium regime in the linear regime. And of course you can see that at the deformation close to 60%, you have the transition between linear and non-linear regime. Of course, this transition depends on the nature of nanotube. Here I have used a nanotube with aspect ratio of 150. Of course, this result is valid only for our nanotube. Now we have tried to observe what's happened about this aggregation, and we perform some very simple experiment by optical transmission observation. And the scale of this picture is about 5